Howdy everyone, I'm Lei Wang, a PhD student from Texas A&M University. It is my great honor to be here to present our work, RMax, extending Bélády's mean with prefetching to bound realistic cache performance. The artifact for this work is available, evaluated, and the results are reproduced. Before diving into the main content, I would like to thank the co-authors of the paper, Chahan, McCoy, Gino, Professor Jimenez, and Professor Grass, for their insights and guidance. I would like to thank the anonymous reviewers for their suggestions as well. Cache prefetching has been a hot topic since at least 1978. It is a commonly used technique to reduce memory latency and yields good results. But we do not know how good cache prefetching can be. We do not have a theoretical or practical upper bound on cache prefetching performance. For another hot topic in cache design, the replacement policy, its upper bound has been established since 1966 by Bélády. To bound cache prefetching performance, we seek to extend the Bélády's mean as a starting point. To the best of our knowledge, there is no prior attempt like this to do optimal prefetching. And to make things clear, we are not proposing a microarchitecture that can be built in real hardware, but a technique. Many cache prefetching papers use two baselines for performance comparison. One baseline is a cache without prefetching and uses LRU. It is used to highlight the gain from the prefetchers. Another baseline is a perfect cache that always hits and is used to show how much headroom is left. However, a perfect cache is not realistic. A perfect cache ignores the very constraint on cache capacity, memory bandwidth, and latency that restricts the performance in which we are trying to overcome here. Our design, RMax, considers those constraints while approximating upper bound. As you can see from this diagram, a perfect cache can be too loose an upper bound for cache prefetching performance. We want to know the gain on a workload with constraints and which workloads are worth pursuing. A constrained upper bound can also guide future cache prefetcher designers, like the Bélády's mean for replacement policies. We do not know how far away the cache is from the constraint. Here is a simple example to show the Bélády's mean for cache replacement. The algorithm works by evicting the block that will not be used the furthest in the future. The circles represent the access stream. The boxes represent the cache state. So the cache starts with blocks A, B, C, and D. The first four accesses produce 4 hits. Address E is not in the cache. When looking forward into the future, A and C do not have any more accesses, so we can choose to replace A or C with E. And address F results in a cache miss as well. When looking into the future, we find out address E and C, they do not have more accesses, so we can choose to replace E or C with F. And address B and D hit in the cache. Replacement policy by itself has an optimum, but prefetching does not. We propose RMax, a cache management policy that extends Bélády's mean to combine both replacement and prefetching. Similar to the Bélády's mean, RMax is omniscient but not omnipotent. RMax has perfect knowledge, but unlike a perfect cache, it is constrained by cache capacity, memory bandwidth, and latency. As you can see from this diagram, we did our experiments on a traditional 3-level cache system. After going through the motivation and the problems we are trying to solve, let's look at how RMax works. Let's go back to the Bélády's mean example. The question will be how to add prefetching to this. One approach is to identify a window that we can initiate the prefetch without evicting useful blocks. In other words, the prefetch must not cause more misses. Go back to this example. As we can see, E replaces A because A has no more accesses. So we can prefetch E the moment after A is accessed. Similarly, we can prefetch F to replace C the moment C is accessed. Both actions will not cause more misses. However, we cannot prefetch E before A is accessed or prefetch F before C is accessed, as this can cause unnecessary eviction of useful blocks. We want to find the earliest time the prefetch can be issued to overcome the problem of limited bandwidth and memory latency. But at the same time, we do not want the prefetcher to be overly aggressive that will lead to eviction of useful data. Rmax works by extending the Bélády's mean. Rmax will prefetch the next miss into the cache to replace the block whose next access is later than the miss. That way, the cache should only retain blocks that will be accessed in the close future. Blocks that are not accessed in the close future, or the dead blocks, will be evicted to make space. We want to make sure only to issue prefetches that will not lead to eviction of useful data. Using the same example and the Rmax algorithm, we reach the following solution. After A is accessed, we look ahead in the access stream and find E will miss. In the cache, only A will not be accessed again in the future, so after A is accessed, we prefetch E to replace A. B hits in the cache, but a more imminent miss is F. F will miss sooner than B's next access, so prefetch F to replace B. C hits and has no more accesses. B will miss, so we prefetch B to replace C. By using this approach, we have greatly expanded the window of arrival for a cache block. If this window is larger than the worst-case scenario of the latency of retrieving the block, we can avoid the cache miss. This window is greatly expanded now. After the simple demo of Rmax, let's look at some difficulties on how to implement Rmax in a simulator. If the call is in order execution and only a single level of cache exists, the memory access stream seen by the cache will not change. The implementation will be straightforward. However, if the system has an out-of-order call with multiple levels of cache, this makes the whole system reactive, and the memory access stream will change, especially when we make changes to the replacement decisions and prefetching. We need a way to deal with the changing memory accesses. To address this issue, we use an iterative approach to amortize the effect of changing memory access to achieve an equilibrium. Let's see what we mean by iteration. First, we configure the cache to use LRU and prefetch nothing. We run the simulation and we record the memory accesses. Then we apply the algorithm to parse the recorded memory accesses to generate prefetch targets. After that, we rerun the simulation, except applying the Rmax algorithm to manage the cache state. Then we check if the IPC is converging. If the IPC is not converging, we will pass the updated memory accesses, apply the algorithm, and run the simulation until the IPC converges or stabilizes. In the end, we will have an IPC that approximates the upper bound for performance for a particular workload. After going through how Rmax works, let's look at the evaluation and the results part. We implemented Rmax on the ChampSim simulator to simulate an Intel Golden Cove-like core with out-of-order execution and 3 levels of cache. For simulations, we use 50 million of instructions for warm-up and 250 million instructions for simulations. For traces that are not same-point weighted, like the CVP1 traces, we use the first 20% of the instructions for warm-up and the remaining 80% for simulation. We evaluated Rmax on a wide range of benchmarks, including SPEC CPU 2017, CVP1, GAP, and XS Bench. Here are the main results. All speedups are normalized to the results produced by running simulations with no prefetches and LRU as a replacement policy. Using the same configuration and workloads, we evaluated on a wide range of prefetches, replacement policies, placing Rmax at different levels of the cache, and always hit cache. Here are the results for existing prefetches. What we found out is that they tend to perform well on a common subset of workloads, and existing prefetches tend not to perform well on a similar subset of workloads. Here are the results on Bélády's mean. As you can see, replacement policy by itself does not provide significant speedup. Existing prefetches can easily exceed them. Here are the results for placing Rmax at different cache levels. Rmax is never the best in L1 because capacity matters. Rmax performs best in L2 as the L2 cache is a good compromise between speed and capacity. Rmax in the last level cache is not as good as L2, and it can be caused by the slower operating speed of the last level cache. Here are the results for always hit caches. Always hit L1D of course yields the highest speedup because it does not reflect on capacity and latency. So, while perfect cache shows L1 is the best place to place the prefetchers, L2 is better with constraints. Here are the results for L2, and again, the results confirm that always hit cache can significantly overestimate the potential space for improvement. For example, PRU rent from Gap benchmark suite shows that on realistically 678% speedup with an always hit L2 cache, compared to a no prefetch LRU baseline, while Rmax in L2 shows a speedup of only 21%. And sometimes existing prefetchers can get most performance achievable by Rmax for some workloads. For example, 649 Photonic 3D from Spec CPU 2017 shows a speedup of 53% with Rmax in L2, and with SPP, the speedup is 35%. For graph workloads, especially those from the Gap benchmark suite, existing prefetchers tend not to perform well. Let's look at the final section, the analysis and conclusion part. As we see from the previous slides, Rmax performs well and has taken the constraints into consideration. We now want to understand what prevents existing prefetchers from achieving Rmax performance. The coverage comparison shows that Rmax can eliminate most of the cache misses compared to a prefetcher like SPP. But there are many other factors that can affect coverage and the overall performance. Is it simply because existing designs cannot generate correct addresses? Or is it because prefetchers are not issued at the opportune time? Or is it because of the wrong replacement decisions? Here, we introduce SPP Max and Bertie Max. They are variants of Rmax. We use the correctly predicted addresses from SPP or Bertie to drive Rmax. SPP Max prefetches all the prefetches using the same algorithm before and manages the cache the same way as Rmax does. It's the same thing for Bertie Max. By doing this, we only focus on prefetcher's ability to generate correct prefetchers because timing and replacement have been taken care of. The diagram shows the speedup of increasing memory bandwidth, increasing the cache capacity, and reducing the memory latency. We multiply the available MSHRs at all cache levels with 100 to simulate the effect of large bandwidth. We do not see huge speedups by increasing the bandwidth only. We multiply all levels of cache by 100 and see significant gain. However, what is interesting is that for compute-int workloads, Rmax in L2 with a small cache size can achieve almost identical performance compared with huge cache size. And we use an always hit cache to simulate the effect of zero latency and infinite capacity, and this overestimates the gain. Again, with realistic constraints, L2 is ideal to place a prefetcher. With proper management of the cache, the gain can be significant, even without huge cache or large bandwidth. This box plot shows the timeliness information. The vertical axis represents the number of cycles that a useful prefetch runs ahead of its demand. The results show that useful prefetches need to run very far ahead of time, with some upper bounds approaching 100 million cycles. We also see that while in general, Rmax timeliness is higher than most prefetches, its range is similar. From this work, we showed that a perfect cache is too loose. Our design, Rmax, approximates the constrained upper bound. And Rmax shows that not all workloads display the same space for improvement. And even for a small cache like L2, a high coverage over 90% is possible. And L2 is better place to place a prefetcher compared with L1. And also, prefetches need to run very far ahead of its demands. Thank you very much for your time.